Hello, welcome back to the second video of the 7.4 Proving Trig Identities. Now that we have done some preparations on the proving, so now when it comes to the actual proving the trig identities, we just have to make sure that the question, the left side has to be equal to the right side. So this is our goal to when it comes to the proving. Because you will always get an equation that will have a left side and a right side. Okay, so our job is to make sure that they both sides are equal. So the initial step that we must consider whenever we're getting a proving question is to look at the left side and the right side, and we have to choose. We have to pick one side to start a proving. Okay, so sometimes it's the left side, sometimes you will pick the right side. So if you are in this example number one, I'm going to pick the left side because the left side is the signs that with the longest, like that will also allow me to do more things. Okay, you will never pick a side that is too short or there's not much that you can do about it. Okay, so such as a secant squared x. All I know about the secant x is that this is the reciprocal of the cos x. Okay, after you convert this into a 1 over cos x, there's not much that you can do to turn that into that is equivalent to the left side. So that is the reason why I always pick the longer side, the ugliest signs to start my proving, because those are the signs that I can do more on it. Okay, so for example number one, once I have chosen the left side, then I'm going to rewrite the left side like what I just did over here, and then from this step, then I will go further, and hopefully at the end it will turn into equivalent to the right side. Okay, so what we know about the tangent is that tangents can go further in terms of a sine or cosine, right? So tangent square x will become a sine square x over a cos square x plus the 1. Okay, and then of course when you're adding a fraction with the whole number, you're going to do a common denominator. So common denominator cos square x. So I will have a sine square x on the top here plus, okay, then a cos square x. Okay, because a cos square x over cos square x give you the 1. And from here, then always keep the Pythagorean identities in mind. So now I know that a sine square x plus a cos square x will give me 1. And denominator cos square x, and 1 over cos square x in fact is equal to the secant square x. Okay, so therefore I can say that now this is equal to the right side. So now I start with the left side, and now I say now is equal to the right side. So I'm done. So I have proven this question successfully. Okay, so move on to example number 2. So again, proving the left side, 1 plus tangent theta over 1 plus cotangent theta equal to the right side tangent theta. Then by looking at this, I'm sure that you know what to pick. Obviously, I'm going to pick the ugliest side, the fractions, right, with the tangents over the cotangent, you know, instead of choosing the right hand side. So right hand side I have so the left hand side, this is what I have chosen. So I'm going to rewrite this. Okay, I'm going to rewrite what is on the left side, and then I can continue proving it. And of course what I can do with the tangent, or what I can do with the cotangent, is to convert them in terms of a sine and a cosine. So I will be doing this. Okay, so I'm not going to carry a fractions over another fraction, so I'm going to do like this with the brackets, So cotangent is the other way around, so it's a cos theta over the sine theta. Okay, then I'm going to do a common denominator. Okay, so I will have a cos theta plus a sine theta. And don't forget, this is not the Pythagorean identities because this one is not a cos squared theta plus a sine squared theta, okay? So be extra careful and divide it by. And again, you will have a common denominator of a sine theta. And so you will have a sine theta and plus a cos theta. Okay? So now when you change these two fractions by flipping the second one, so you have a sine theta at the top here and a sine theta plus a cos theta down here. And now you know that this is the same, so I can just cross it off. So what I ended up with, it's just a sine theta over cos theta. And that, in fact, is equal to a tangent theta. And that is exactly equal to the right-hand side. Okay, so I started with something long and ugly, but I ended up with something simple and one term, tangent theta. Okay? In my example number 3, again, continue. Between the tangent theta plus the cotangent theta equal to secant theta times a cosecant theta. Sometimes you have a choice to pick either one, but I will still, in this case, I will still trying to pick the one with the reciprocal ratio, because I always think that the reciprocal one, there's more things that you can do about it. Okay, so I have a tangent theta plus a cotangent theta, and when I convert the tangent theta in terms of a sine theta over cos theta, and then a cotangent theta becomes a cos theta over a sine theta. Okay, from here I can do a common denominator. When you do a common denominator, you multiply the two together, and then on top here you will end up with a sine squared theta, and over here you will end up with a cos squared theta. Okay, now those are the Pythagorean identities. So I ended up with a 1 over the cos theta sine theta. Okay, and if you think about if you want to separate this, so this will becomes a 1 over cos theta times a 1 over a sine theta. Okay, if you look at what you really aiming to prove is that the other side has to be equal to a secant theta times a cosecant theta. And you know that a 1 over cos theta will give you, is the same as the secant theta, because secant theta, the reciprocal is 1 over cos. And also, when you multiply by 1 over sine theta, this in fact is the cosecant theta. Okay, so when you multiply, you can put them together. So that is exactly equal to the right side. So again, I have just successfully proven that the two expressions are equivalent. Okay, moving on to our example number 4. So now you're proving something that is a little bit more complicated. Now you have a sine 4 theta plus a cos 4 theta, okay, equal to 1 minus 2 sine squared theta cos squared theta. Well, in this case, both of the sides are equally long or ugly, but I'm sure that people might want to still pick the one with the exponents of 4. So you can pick either one. Okay, so let's pick the left sides again. Okay, and I can also do that by well, because there's nothing I know about the sine 4 theta or cos square theta, but I know that a sine square theta and a cos square theta can be replaced by another expression. So maybe I can try to do something like this. Okay, so I can have a sine square theta to the power of 2 plus a cos square theta to the power of 2. And what I can do for the sine square theta, because of the Pythagorean theorem, because of the Pythagorean identities, okay, the sine square theta plus a cos square theta is equal to 1. So I know that I can replace the sine square theta with the 1 minus a cos square theta. So down here, if I'm going to replace this with a 1 minus cos square theta, okay, to the power of 2, and then, well, in fact, I don't have to break this into 2. I just have to leave this as a cos 4 theta. Yeah, I shouldn't have done this from before, because what I'm trying to make is I'm trying to make this expressions, everything is in terms of cos, so I don't really need to change that. So when I expand this, okay, when I expand this with a binomial, perfect square binomial, I will have a 1 and minus 2 times a times b, so I still have a cos square theta, and then I will end up with a plus cos 4 theta. Okay, and then I'm going to adding this cos 4 theta at the end. Okay, and so I will have 1 minus a cos square theta, collecting like terms here, and I will have a plus 2 cos 4 theta. Okay, now so with that I can go further. Well, by looking at what I have on the other side, I have a 1 minus a 2 sine square theta cos square theta. I have a cos square theta here, and I also have a cos 4 theta there. Okay, so what I can do with that is that if I'm going to take 1 minus, if I take the 2 cos square theta as a common factors, okay, there's one thing I forgot over here, that when I expand this, this is supposed to be a 2. So I'm missing a 2 here. Okay, so I'm missing a 1 to the 1 and a minus a 2 times cos square theta. So I'm missing the 2 cos theta here. Okay, so that's how I get my common denominator, a common factor, sorry. Okay, so 1 minus a 2 cos square theta, if I take a 1 minus a cos square theta, I'm getting this back. Okay, a minus 2 cos square theta times 1 give you this, and a minus 2 cos square theta times a minus cos square theta, I'm getting a positive but 2 cos 4 theta. Okay, so what I can do here is that finally I'm getting a 1 minus 2 cos square theta, and this 1 minus cos square theta really is the sine square theta. Okay, so that now I can see that this is going to be equal to the right hand side.